In this problem, we are going to look at a simple rigid Euler buckling problem. And so as you can see, our givens are that our spring stiffness coefficient is going to be 2 kips per inch, with our springs located at points C and D, and the h variable in this case is going to be 2 feet. And as in all rigid Euler buckling problems, we are going to be solving for our critical load P applied to the system. And so the first thing to do is to write down any important equations that we can use in this problem. And so the main equation that comes to mind when using rigid Euler buckling problems is the force in the spring. So that equation is called Hooke's law, and it's that the force in the spring is going to be equal to our spring stiffness coefficient times the deflection of the spring. And so this is going to be our main equation for this problem. Other things that we want to keep in mind are that we are also this is going to be a static problem, so we can say that our sum of the moments is going to be equal to 0, so we'll use that to our advantage. Another important assumption that we make, not necessarily an equation, is that the sine of theta, in this case, theta being the deflection of the whole bar, that theta is going to be approximately equal to just theta. So we're going to use that to our advantage as well. Have our important equations down. The first step is to draw our free body diagram. So our free body diagram is going to look a little bit something like this. We will have a straight line. We're exaggerating the deflection by a lot so that we can solve for the different variables. And so we have reaction down here. We have our force P at the top right here. And then this right here is going to be our point B. Right here is our point C. Here will be point D. And at the bottom we got point A. And so in all free body diagrams, the first thing we're going to have is going to be 2 reaction forces at the bottom, which will be R1. And we'll also have R2, and in addition to this, we are going to have 2 forces applied at D and C due to the deflection of the spring. So right here we're going to have a force of F1, and right here we will have a force of F2. And so now we want to look, so let's define what theta is in this problem. So theta in this problem is going to be this angle right here. And then the other thing we want to look at is the distances that our springs are deflecting by. So we are going to call those these distances. So up here we'll call this distance D3. The distance between the spring and point C we will call D2, and this last distance we will call D1. And another important thing we have to add to our free body diagram is the heights. So this height is going to be h, the point up to C is going to be 3h, and the point all the way up to B is going to be our 4h. So now that we have our free body diagram, we can start looking and solving for what our distances are going to be, and then subsequently what our forces and our springs are going to be. For rigid Euler buckling problems, we assume that the theta is going to be approximately equal to the sine of theta. We can write out what our distances, our D1, D2, and D3 are going to be. So D1 in this case should be the height, which is h times theta. Our D2 is going to be equal to 3h times theta, and D3 is going to be equal to 4h times theta. And so now that we have those distances, we can find what the forces are going to be. And so the forces, we just have to use Hooke's law, which we stated right here. And so for F1, it's going to be equal to K times whatever deflection it has, which is going to be D1, which that is equal to KH theta. And then our F2 is going to be equal to k times d2, which is going to be equal to 3kh theta. And so now that we have our forces defined and our distances defined, we can go ahead and take a sum of the moments. So now we are going to take a sum of moments about point A. And so we're just going to write that as this, and then I'm going to assume that clockwise is the positive direction, just so that we can keep track of our positives and negatives. So moment about point A, that's going to be equal to 0. And so to start off, we have, we'll start with our P, that force, times a distance of d3, since that's the distance at the very top at point B. That is going to be minus the force F1. F1 is going to be multiplied times the distance from point A, which happens to be h in this case. And then this is also going to be minus F2 times the its distance from point A, which happens to be 3h, and all of that is going to be equal to 0. So now we can start plugging some values in, and so for P we don't know, so we have P times our D3, which happens to be 4h theta, minus our F1, which is kh theta times h, minus F2, which is 3kh theta times 3h, all of that equal to 0. And now when we look at this, before we start plugging in the values for k and h, we can get rid of a theta, since each term has theta. We can also get rid of an h, since each term has at least one h. And so now that we simplify that equation, our equation looks like this. It'll be P, 4p minus kh minus 9kh is going to be equal to 0. And so if we solve for p, we will get p is equal to 10kh over 4. So now we can start plugging in our values. So we have 10 times 2 kips per inch. This times 2 feet, and since this is in feet, we're going to want to convert to inches. So we have 12 inches per foot. All of this over 4. And then we can solve for p, and so we get p is going to be equal to 120 kips. And so this is our final answer. Thank you for watching.